in the phase domain, rather the block diagram we have is that of a phase detector. Okay. We compute the difference in phase and we pass it through two paths. A proportional and an integral path. Add them, okay, and feed this to the VCO. And VCO has a proportionality constant K VCO between the output frequency in hertz and the input frequency in input voltage in volts. Okay. So this simply is the phase difference between the inputs to the phase detector. We also looked at the implementation of the phase detector. We implemented using a 3-state machine. That's the reference and that's the output. Okay. Now, the advantage of this system is we can have a DC, or if you want a DC here, you don't need a non-zero, you don't need a non-zero input out of the phase detector. The integrator can have a non-zero output with a zero input. Okay. So the phase difference between the reference and the divider output is 0. So now you are not limited by the range of the phase detector anymore. Okay. So in steady state, this needs a DC to force the output frequency to be the appropriate value. Okay. And that is supported by the integrator. Now any rapid changes in phase will be corrected by the proportional path. So if you know the control systems, this is known as a PI controller, right? Proportional integral controller, and that's what it is used for. The integral part is used to suppress the steady state error. So the more integrators you have in the loop, the more it follows the input in steady state, right? If you have one integrator, it follows a step in that is in the long term. If you have two, it follows a ramp and so on. So in this case, we call it a type 2 system because in terms of phase, the VCO is also an integrator. Okay. Now, to make, you have to insert zeros so that when the gain rolls off to unity, it does so with a 20 dB per decade slope. This is to ensure stability. If you have multiple integrators in a loop with no zeros, it will become an unstable system. Okay, you will end up with poles on the imaginary axis. Okay. So for that, so in this case, this two-path structure, this proportional path and integral path will give you a 0. What will be the frequency of the 0? KPDI by? KPDI by KPD, yeah. So there will be a 0 and that has to occur before the unity gain frequency of the loop. Okay. So this will account for all the slow changes and steady state, and this will provide negative feedback correction for rapid changes. Okay. So in the phase domain, in terms of the phases of signals, we have this model. We take the difference So this is the control voltage of the VCO and this is the output phase of the VCO. Okay. this is the model in terms of the phases. So the gain around this loop, or the loop gain, is okay. So at low frequencies you will have this term and this term. So you will have 1 over S square behavior. At high frequencies, the first term here becomes negligible as the magnitude of S keeps on increasing. It's KPD times 2 pi KVCO by NS, exactly what you had with the first order, type 1 phase lock loop. Okay. So then it is a single pole or a single integrator. It shows the behavior of that. Now you can also add additional poles to suppress the reference feed through further. Okay. Now, like we can add more poles. The only thing we have to keep in mind is the stability criterion, that when the gain crosses unity, the slope of the roll off of gain should be 20 dB per decade. Okay. So for instance, I want the input to the VCO to be clean. I don't want it to have fluctuations. If it has fluctuations, it will frequency modulate the VCO, which will show up as spurious components in the output spectrum. Okay. So that is like having, instead of a periodic signal which has an impulse spectrum at some frequency, you will have sidebands around it, and the spacing between the main output and the sidebands will be related to FREF, the reference frequency. Okay. See, this system is periodic with FREF because it's driven with a signal at a frequency FREF. Okay. So when you look at any signal in this, it will be periodic with FREF. Now you have to reduce the strength of the component at FREF at the input to the VCO. Okay. So you can insert additional poles. I'll show one pole, but it could be more than one if you need more attenuation. So the transfer function of that additional block should be such that at FREF you get additional attenuation. Okay. But it should not affect the phase margin of the loop, or meaning it should not affect the slope of the magnitude roll off at the unity, at the 0 dB crossing of the loop gain. Okay. So if I plot the loop gain, what I would like to have is at medium frequencies, I'll have a first order behavior, and this is given by this term, the second term in this. So if I add the other pole also, I will have, okay, or maybe I should call it P3 because this has 2 poles at the origin. Okay. So this is the expression for loop gain. So this part represents these two terms. Okay. So I am assuming that the third term here is approximately 1 in this range, and the first term is negligible. Okay. KPDI by S. And this comes into picture at low frequencies. And the frequencies before which this is dominant is, okay, what is the unity gain frequency under these assumptions? So this part, right, we are saying that this is the part that is significant in this region. So whatever is the numerator of that function is the unity gain frequency. Okay. And this P3 must be beyond that. and for it to be useful, this omega ref or 2 pi times f ref must be somewhere here. It's only then that this extra pole, this P3 will give you additional attenuation, right? If your omega ref was here, then it's not doing anything for you, okay? So you can have more poles, but they may not help because they have to be between the unity gain frequency and this. They should not affect the phase of the function at the unity gain frequency too much, but they should provide a lot of magnitude attenuation at omega ref, okay? So you can have 1 or 2 additional poles and that will give you a lot of attenuation and you're home free, right? Okay. So this, we kind of started by constructing a first order system and then added a second integrator to improve the DC performance and a third pole to improve the attenuation. So the conditions become very clear here, that is condition for stability and so on. These points should be in this order basically, right? KPDI by KPD, this should be significantly less than this, so that it shows a first order behavior here. So this should have a first order or 20 dB per decade roll off, okay? And P3 should be less than the unity gain greater than the unity gain frequency clearly, because it should not affect the phase of the loop gain at unity gain frequency. And omega ref must be greater than P3, otherwise P3 is not doing anything, okay? So this KVCO is typically given, that is you design an oscillator and you find out what KVCO is. You have some freedom to adjust it, but not a whole lot of freedom, okay? You can adjust it to some extent. Now given KVCO and N is given, that's a system requirement. You are supposed to generate like 1 gigahertz from 1 megahertz, then N is 1000, there is no playing around with it, okay? So then after that you can decide the rest of the parameters, and FRF is also given, okay? So based on these things you can determine the remaining parameters, okay? Any questions on this? This part is quite simple, right? So just to choose the system parameters so that it is stable. Now there are some other constraints, like we'll come to that soon. Since we say that this has to be less than this and all of this, we can make all these three very small, okay? Right, then we have, if for instance instead of the curve being what I drew here, let's say it was shifted to the left, okay? It was like this, it simply moved to the left, that is you scaled all frequencies. What do you think will happen to the PLL? Which is better? Cycling time will increase. Actually, that's a very good point, that the closed loop bandwidth of the red system is much less than the closed loop bandwidth of the black one. So that is an argument for pushing it to the right. Now, if you push it too far to the right, you will have problems with reference feed-through, okay? So if I have something like this, so clearly the attenuation at FRF is the most for the red one and least for the blue one, whereas the bandwidth is least for the red one and most for the blue one. So there is some compromise based on how based on the settling time requirements. If there is no settling time requirement, then you can safely make it very slow and the signal quality will be better, okay? So that is as far as we go now. We will see there are some other effects of it as well, okay? One of the other issues, this is just the plot of the loop gain, okay? And from this you can get the closed loop gain and other transfer functions. Now every component in the phase log loop is non-ideal. It will inject some kind of non-ideality at the output in addition to its ideal output. So what you have to evaluate is the transfer function from every one of those non-idealities to the output and see how they are affected, okay? Now all of these transfer functions from anywhere to the output will have the same poles, but they will have different zeros, okay? So we have to evaluate those things also before we see whether to make for instance this particular value small or large, how large we can make it and so on, okay? So just a quick summary of the PLL. you use basically the phase frequency detector, that is the 3-state detector, has become the standard. So, we will assume that that's what we will use. We will typically not use XOR gates and so on. So, that is mostly for playing around. You don't use it in practical systems. Okay. So, this is 3-state state machine. What is the what is the gain of this phase detector? So, let us say the phase frequency detector gives you either 0 or 1 volt at its output, right. It has up and down outputs and it gives you either 0 or 1 volt. Okay. What is the gain of the phase detector? 1 by 2 pi. Yeah. So, if the output is 0 or let us say Vp volts, the output, the gain of the phase detector will be Vp by 2 pi volts per radian. Okay. We will see how to make the integral part soon. And the VCO has some kVCO in hertz per volt. Okay. Why does it do this? And the divider has a modulus n. Okay. And we also have another constant of the phase detector, which is the integrating path constant. And what's the dimensions of this? Volts per radian. Volts per radian seconds. Is this correct? Yeah. Now, given all this, you will have the loop gain will have 2 poles at the origin. Okay. 0 at kpdi by kpd radians per second, a unity gain frequency of 2 pi kpd kVCO by n radians per second, and if you have additional poles, it will have that as well as the poles. Okay. So, you can have poles at P3, 4, etc. Okay. Now, of course, all this assumes that they are in the right order. Okay. So, clearly, if you have the other P3 and P4 very close, then the unity gain frequency will not be this, but that's not a useful system, so we don't have to worry about all of that. Okay. So, now we can go on to see how to implement the PLL. We have seen some parts of it already. Okay. We have seen how to implement mainly the phase frequency detector. I am not going to cover the frequency divider. You know how to make a divider using state machines, right? So, if you want to divide by n, you have to have at least n states, and you need to write a state transition table and come up with a digital circuit to do that. And there are systematic ways of doing this. And typically, in a frequency synthesizer, n has to be variable. That is, you may have to generate different frequencies from reference frequencies. And in some cases, the same system may have to operate with different reference frequencies and give out the same output frequency. Okay. So, this depends on the system. For instance, you use a sound card, and in some systems the sampling rate is 48 kilohertz, in some it is 44.1 kilohertz and so on. So, these are, you don't have to, obviously, you can't expect the external system to always give you one particular frequency. Whatever it is there, you are expected to use it and generate the right frequency for your use inside the chip. We are not talking about sound cards, but the idea is similar. If you have your Ethernet card plugged into something, the reference frequency available may be different if you plug it into one PC or the other, or some platform and some other platform and so on. Okay. And it also depends a little bit on availability of other components. Maybe in some cases, some reference frequencies are available more conveniently because crystal oscillator modules are available for those frequencies. So based on that, you may have to vary n. Okay. And finally, I mean, the same system may have to work at different data rates. Like we have a digital system, if you want to make it work at different data rates, you have to change the rate of the clock. Now this synthesizer is used to generate the clock. If you have to change the clock frequency, you have to change the division modulus in the feedback path. Okay. So that part I am going to completely not cover here because I think your digital circuit design skills should be able to take care of that. Okay. You can make a programmable divider by having some combination logic and some certain number of flip-flops. Okay, the next thing is to make this part of the circuit. Right? How do we do this? We have something that takes the phase difference, but it gives you two outputs. If you take the difference between the two outputs, it gives you the average value of it is the phase difference between the inputs. Okay. Now we need something that takes the difference between the two outputs of the phase detector, as well as generates this functionality. How do we go about doing it? So we have the 3-state phase detector. I will call this up down in anticipation of what it is going to do to the VCO. Okay. So up minus down will give you the phase detection output. Okay. The average of up minus down is related to the phase difference between A and B. Now we have to firstly take the difference between up and down, and also we have to realize this KPDI by S plus KPD times that. Essentially that voltage has to go into the VCO. So at the output we need a control voltage, and this control voltage must be related to okay. How do we go about realizing this? Huh? No, it's up minus down, right? No, we don't further average it. So that's where we covered the non-ideality of the phase detector, right? So we said that we first imagined an ideal phase detector which gives you a DC based on the phase difference. With that we came up with the type 1 PLL. But then we also looked at a real PLL and said it has periodic disturbances in addition to the average. And those periodic disturbances created output spurious components which were too large in magnitude. Now in this also there will be that periodic disturbance in addition to the average. We simply have to go and figure out what the effect of that is on the output. Okay.
In that PLL, we had disturbance because we did not.
Yeah. I mean, how long will you average? There will always be disturbances, right? Maybe you will change the magnitude of it. Okay. So averaging is the same as inserting another pole. Okay. If you have a certain frequency, a certain periodic disturbance at a frequency FF, and you pass that through a low pass filter whose pole is at some frequency less than FF, if it is much less than FF, it is like averaging that. Okay. That's what we have done here effectively. Okay. So how do we generate this? How do we generate this part? The integrator plus RC parallel. Okay, the complete circuit. How do you realize something like this? Oh, you need R, C's, both of them, series, parallel, something else. Any other components? What is an integrator like? If you see an integration, what would you use? What component do you need? Yeah, it has to be a current into a capacitor or voltage across an inductor. And inductors are hard to realize, so we generally rule them out. Okay, so it has to be, I mean, the integration in in analog circuit design is realized using a current flowing into a capacitor. Okay. Okay. Okay, so we have so far, so what he says is, we have a current proportional to up and a current proportional to down. Okay. So when it is up, it will get integrated. So the voltage across the capacitor will increase. When it's down, it will decrease. Okay. So this part only realizes this much. How about the other one? Huh? R in parallel. What were you saying? Yeah, so how do I realize this? It can be an R in series, right? So, see, if for this I can do this, okay? And if I wanted this part plus this part, I can substitute a resistor for this capacitor, okay? I can have this up minus down current flowing into a resistor, okay? Now I need to add these two voltages, okay? I realize that the same current is flowing through the capacitor and the resistor, so I can just put them in series, okay? So the way it is implemented is, we have the up and down outputs from the phase detector. And you have these switches, okay? So these two are identical current sources. Don't worry about what happens when the switch is open, right? It looks like the current source is being forced into an open. You can have another switch to ground or something. You can deactivate the current source in some way. So to keep the diagram simple, I'm going to keep it like this. Okay. So now what is and this is driven from a 3-state phase detector, okay? So what is KPDI, what is KPD for this combination? So this is the control voltage to the VCO, right? Huh? KPDI? It has to have dimensions of volts per radian, the KPD, and the other one is volts times radians per second by radian, okay? So we just have to look at what happens if you have so when up is high, ICP will flow into this. The voltage across this is the proportional output in the controller. It is ICP times R, okay? And this is a ramp which will go up at a rate ICP by C, okay? So simply KPD is ICP times R and KPD times I is ICP divided by C, okay, and it has the right dimension as you can see. Where is the 0? Yeah, the 0 is at KPDI by KPD, which is 1 over RC1 radians per second, and that anyway you can simply look at the circuit and realize that that's where the 0 is, okay. Now this goes to the VCO. So what happens is, see, to change the free running frequency of the VCO, you need an average input at the average control voltage at the input of the VCO. So after steady state is reached, the capacitor will have accumulated some charge, and that will provide the average input. And if there are fluctuations, if there are pulses of up or down, the voltage across this capacitor will be small. Okay, that will be the meaning of having the 0 here. Okay, so 1 over RC1 is much smaller than 2 pi FRF. Okay, so if you have fluctuations at FRF, that means that effectively the voltage across the capacitor is much smaller than the voltage across the resistor. Is that part clear? Is that okay or no? So 1 over RC1, which is the 0, is this. Okay. Now, if you look at this, the impedance of the capacitor at this frequency is 1 over 2 pi FRF C1. Okay, and that is much smaller than R. So if a current pulse at a rate FRF is flowing into the series combination, the impedance of the capacitor is much smaller than the impedance of the resistor. So the voltage across the capacitor is much smaller than the voltage across the resistor. So for fluctuations of FRF, it's the resistor that matters. Okay, the capacitor is as if it's not there. So we said the same thing by showing the loop gain plot and saying that the 0 is much smaller than FRF and so on. But in terms of currents and voltages, this is what it means. Now, if you have some kind of an average up minus down current, then that will accumulate charge in C1 and the voltage will drift up or down depending on the sign of up minus down. Okay. So it will finally reach steady state where the capacitor holds the value required for the VCO to oscillate at some frequency, and the resistor will supply the fluctuations. Okay. So this is quite simple. I mean, this is, you can make this integrator plus proportional combination using op amps and so on. Okay. So for instance, if you pass currents through circuit like this, or you can have more complicated circuits which do the same thing. Using an op amp, you can make an integrator and you can make a summing amplifier. So you can make any of these combinations with different constants. Okay. Typically, you use a very simple circuit here because these circuits also add noise. You don't want to make them very complicated. That's why you use the simplest possible thing. Some cases you may have to use more complicated stuff because the size of these components may become unmanageable. Okay, when you try to realize it on an integrated circuit. So in that case, you may go for some fancy circuit which perhaps adds noise but reduces the size of the circuit. Okay. So we will not worry about that. This is the simplest realization because you have up and down. To get the difference, you simply have current sources connected to the node. That's the simplest way of getting difference in the analog domain. Difference or summing. You sum currents. Okay. In this case, currents are of opposite polarity, so you get the difference up minus down. Now, the up minus down current is passed through a series combination of a resistor and a capacitor, which respectively give you the proportional output and the integral output. Okay. And the series combination does the summation. So this is the absolute simplest realization of the phase detector and loop filter. So this part of the circuit is known as the loop filter. It's hard to distinguish, but yeah, something like this. So all of this is known as a loop filter. Okay. Now let's say I wanted to reduce the reference feed through further. Okay. Meaning I want to have this extra term. Where did I have it? Yeah, this part. I want to have this also. Extra pole. How would I realize that? Would I need to go to a completely different circuit or will? Would I? Put a capacitor in parallel with the whole thing. Okay. So the suggestion is to Okay. What is the transfer function of this? Where is the pole? Where is the 0? Will it not change the original circuit because we have connected another capacitor across this? It won't be RC. What won't be RC? No, first of all, there is no pole in this, right? It is the pole of this is at the origin, okay? Because it has a current input and it will go on integrating. So the transfer function originally was KPD I by S plus KPD, which basically was ICP R plus ICP by SC, which basically is ICP R okay, or maybe I should write it like this. It has a pole at the origin and a 0 at 1 over C1R, sorry. Okay. Now, what's the transfer function of this? Will have a pole at R into C1 plus. There is no pole here. There is a pole is at origin, so it will move to R into C1 plus C2. Is that what you are saying? Huh? P3. P3 will be at. So, you mean 1 by this. Okay. Is that correct? 0 should remain the same. Okay. So, the transfer function will be ICP by SC1 1 plus SC1R 1 by 1 plus S R C1 plus C2. Is this correct? Does everyone feel this is correct or is there a dissenting voice? What is wrong with this? Where is the 0 in relation to P3? Where do we want P3 in relation to the 0? Well after the 0, right? So you have the 0 first, then the unity gain frequency, then P3. So where is So actually this is driven by a current source, right? You can realize the natural response by simply opening this and seeing what capacitance appears across R, and that is the series combination of C1 and C2. Okay. So it's not this, but it is 1 plus S R C1 C2 by C1 plus C2. Okay. And that's it, nothing else changes. What is the transfer function at very low frequencies of this? If you input a DC current, DC to the system, what is the rate of the ramp? Should say C1. Why only C1? So the current will flow into C1 plus C2, right? So the rate of the ramp is? Okay. Previously it was flowing into C1. So this is the ramp that you see at low frequencies, and that has changed. Okay. Is this clear? The low frequency part of it, which was this, now this came about because previously if you feed in a current, it flows into C1, it gives you a ramp at a rate ICP by C1. In this case it will flow into C1 plus C2. Okay, so it will give you a ramp which goes at a lower rate, ICP by C1 plus C2. Okay. Now this is the 0 is at C1R, that's basically the frequency at which the impedance of this branch becomes resistive, and that is still the same because the series components are the same. Okay. Now this, so if it is designed properly, what should happen is at very low frequencies you essentially see a capacitive impedance C1 plus C2. At some higher impedance you see R. Okay, C1 is a short, but C2 is an open compared to R. C1 is a short compared to R, C2 is an open compared to R, so you simply see a resistor. So that is the part where it is rolling off at 20 dB per decade, okay, in the loop gain plot. And finally, the impedance of C2 becomes lower even than R. Okay, what is that frequency? It will be 1 over RC2. Okay, so beyond that frequency, it will look like a capacitor of value C2. Okay, now this is only approximate, so this will tell you that the pole is at 1 over RC2, but it's really at 1 over R times C1 series C2. So in reality, what happens is the value of C1 is very large. Okay, because you need a low frequency 0, and C2 is very small. Essentially, C1 should be a short compared to R at the unity gain frequency, and C2 should be an open compared to R at unity gain frequency. Okay, so C2 is smaller than C1. Okay, so this third pole is approximately, it's okay to say this is approximately 1 over RC2. Okay, the series combination of C1 and C2 is approximately C2. So this is an intuitive way to check the answer, but you can derive it quite easily. So if you have and you have a current source I and you have a voltage output V, and V by I is simply the impedance of this part of the circuit. Okay, what is that? The impedance is the reciprocal of the sum of admittances. So this is the admittance of this branch. What's the admittance of this? Okay. So this will give you and this will in turn give you SC1 plus SC2 plus okay, and this is, it's convenient to write this as okay. So this is a transfer function which has the dimensions of impedance. So at low frequencies it's 1 over S C1 plus C2, okay, and it has 0 at C1R and a pole at 0 at 1 over C1R and pole at approximately 1 over C2R. Okay, assuming C1 is much greater than C2. That's how it should be, right? So from this you can also figure out all the constants and pick the values of RC1 and C2 correctly. Okay, so you have KPDI and KPD, and you know how to relate these two. I mean, given some FREF, you know how to get these things. Okay, now there aren't enough constraints without having also a constraint on settling time, but that's okay. Let's say we'll keep the unity gain frequency as small as possible. Okay, that will give you a slow settling, but we don't care for now. Now we also know ICP, R, C1, C2. So actually you also know P3, right? So these can be related to this. So you design a loop, let's say in MATLAB or something, and obtain the values of KPDI, KPD and P3. That's convenient for you. And then you can choose the component values properly. Okay. Now obviously you can, the actual transfer function will have, this is V by I. So you'll have ICP, so you can reduce ICP and increase the value of R, reduce the values of C, everything will remain the same. That is simply scaling the circuit. Okay. So if ICP was 10 microamp and you had 1 kilo ohm and 100 picofarads, you can make it 5 microamps, 2 kilo ohms and 50 picofarads. The transfer function will be exactly the same. Now how do you choose between the different alternatives? So the 50 picofarad one will have a small area, right? If you have smaller components, you have smaller area. That is one constraint. But it may get harder to realize a smaller current source. You will get mismatch, etc., and maybe more noise. Okay, so there will be trade-off there also. Okay, so we now know how to make the phase detector and the loop filter. Okay, the frequency divider we dispensed with. VCO we will see afterwards, but for now let's assume that we simply have a block which gives you a varying frequency in response to a varying input voltage. Okay. So let's go back to the original motivation for coming to the type 2 PLL. So type 1 PLL, we saw that reference feed through was a big problem. Okay. So when we reduce the reference feed through to some manageable level, like 1% of the main carrier level, and that itself is not very good, the range was very small. What is the reference feed through in a type 2 PLL? Okay. So this is so here I am talking specifically about the 3-state phase detector. Okay. This is up, down. This comes from the divider, and let's say we have this standard loop filter. Okay. So what is the reference feed through? The phase detector output effectively, which you can think of as the current here. Okay. The current here is the phase detector output. It's the difference between the currents because of up and currents because of down. Okay. So that had an average value representing the phase difference and a periodic disturbance that depended on the phase detector design. Okay. What is the periodic disturbance in this case? How do you find the periodic disturbance? Yeah, that is one, right? I mean, it's a digital. No, think of the phase detector as a separate component from the loop filter. Okay. I am talking about the periodic disturbances in I out. So the loop filter shouldn't really come into picture. Right? The transfer function of the loop filter. That's how our model is, right? We have what is this? Okay. So this is the model, and originally what we had was we didn't have the integrating path, but we had the rest of the stuff. And the phase detector was ideally modeled by this, but in reality it also had an additional input, E of t. My question is, what is E of t in this case, in this particular type 2 PLL? In case of type 1 PLL, we found the phase difference, we found that it was some kind of square wave, and we found what its amplitude was, etc. What is E of t in this case? Yeah. Yeah, so what will be the E of t? Huh? Same as what? 0. It is 0, right? Because the type 2 PLL will lock with 0 phase difference between the inputs. If you have 0 phase difference between the inputs, the up and down pulses will be infinitesimally small pulses. Okay? So not only, we came up with the type 2 filter to improve the type 1 PLL, type 2 PLL to improve the type 1 PLL, but it also in steady state reduced the reference feed through to 0. Okay? So we made all these arrangements, like we've increased the lock range for sure by introducing an integral path, and we can further suppress the reference feed through using a third pole. But it looks like the reference feed through error itself has gone to 0 because of the different steady state conditions of this loop. Okay? So do we need this P3 ever? Yeah, I mean, see, the phase difference between this and this should be 0. So if the inputs to the 3-state phase detector are coincident, the output will be what? 0. When I say output, I mean up minus down output. That will be 0, right? Is that so or no? Huh? Yeah. Why? I mean, if the input to that is 0, why will the voltage keep varying? Why? Yeah. Yeah, that's correct. So, see, the ideal. Okay, so let's see. So, the operation was like this. If this is A and this is B, you get this. Okay. So, this is up and down is 0. Okay. Now, as I move B backwards and make it coincident with A, what do I get? In the limit, I get just this instantaneous pulses with 0 area, basically 0 energy, right? So, I really don't get anything. Okay. Huh? How? It has 0, right? I mean, it's just a representation, it's not there. If the resetting is instantaneous, it's not there, right? So, here also, see, up and down, when down goes up for a moment and it's instantaneously reset. So, this is what we have in the first case. When the phase difference is 0, both up and down are basically infinite. As you reduce the phase difference to 0, the pulse becomes smaller and smaller and finally shrinks to no area. Okay. So, where is the catch? So, there is no reference feed through at all in this. Huh? There are actually two issues. Firstly, the reset is not instantaneous. Okay. So, what is the effect of that? I think we wrap up now. We'll discuss this in the next class. Okay. So, two things you have to think about are, in the ideal case, this is true, that there is no reference feed through in a type 2 PLL. Okay. So, not only did we increase the lock range and made arrangements to suppress reference feed through, we made the error input itself 0. Okay. But this is with an ideal instantaneous reset. So, there are two things to consider. One is reset path delay. The second is what he mentioned. We use physically different current sources for the top and bottom, right? ICP, we said up controls one current source and down controls another current source. But there are really two different sources. And two different things can never be exactly matched. Okay? Current source mismatch. So, you figure out what happens with these two and we'll continue the discussion in the next class. Okay.